So it is my great pleasure to introduce to you Nora Disis. She is a professor in medical oncology here at the UW and an adjunct professor of pathology, OB, and GYN. She's the Associate Dean of Translational Science. Translational science means the following. If you learn something in the laboratory at the bench, then you can apply that to patients in the clinic. That's translational science. So we're not just learning, oh, the sodium ATP pump does the following. We're learning, oh, if I create a cancer vaccine, I can use it for patients, and it works. So that's translational medicine. So she's the Associate Dean of Translational Science, which means that she's really smart. She's a member of the Fred Hutch. She's the director of the Institute of Translational Health Sciences. So now you got this translational thing down. You guys know what that is now. And director for the Center of Translational Medicine in Women's Health. She's an expert in breast and ovarian cancer immunology and translational research. Her multifaceted research program within the tumor vaccine group includes discovery of new antigens. So you guys got the antigen thing earlier. That's the little foreign body that we want to make an antibody to so we can fight it. So she is she's one of the key players in this tumor vaccine group that includes discovery of new antigens for breast and ovarian cancer and the development of vaccines and other cellular therapy that targets these cancer antigens. She's one of the pioneering investigators who discovered that HER2/neu, so this is a big thing in breast cancer, is you can have this antigen, this protein is stuck on the cancer, it's called HER2/neu. And she realized this was a tumor antigen, and she has developed a vaccine against it. And this is such pioneering work, and a very funny thing happened. My father has a tumor in his parotid gland, a salivary gland, and his tumor is HER2/neu positive. So I called her up last week to see if he would be a candidate for the vaccine. She is the critical face of developing medicine that can make a huge difference for people with cancer. So I cannot welcome her highly enough. She received her MD at the University of Nebraska. She did a fellowship in oncology at the UW Fred Hutch Center, and she's a member of all these amazing oncology task force that are going to turn it around for us. And then there she is with her daughter Maggie, who you can see is the chip off the mommy block. So thank you so much, Nora, for joining us.
So I wish I had information to give you like the last talk. It was chock full of information. I was taking notes. I'm basically going to tell you a story, so you don't have to write down anything. It's not important. It's all research. I'm going to talk about vaccines targeting breast cancer and going from bench to bedside research. That's that translational medicine aspect. And it takes a lot of people to do it. So I'm just one person representing many people who work at the University of Washington doing this type of research. And so what I'd like to convey to you is what it's like to develop a vaccine and what it takes to get a vaccine approved so that people can use it. Outside of having to prove that it works, you have to go through a process to move it from the test tube into animal models and then finally into humans, because you want to make absolutely sure that the vaccine is as safe as possible before you end up going into clinical trials with it. Now, I think vaccines are great, and you heard from the first speaker that vaccines are probably the most impactful medical discovery that has ever been made. And in fact, this is a smallpox patient from 1940. A lot of people died of smallpox. You can see the pox all over their bodies. Not only did they die of systemic infection, these pustules would get secondary infections and they die of overwhelming sepsis. But this disease has been eradicated. There is no more smallpox, and that was because of vaccines and very effective vaccines. Now, the problem with taking the great success of infectious disease vaccines and moving that success into something like cancer is that the immune system does not see cancer as dangerous. And if you think about a virus, a virus sets up signals that tells the immune system, I'm a foreign invader. It's time for you to go all out to try to eradicate me. And pieces of the virus turn on different immune system cells in a very over-the-top way. So we talked about dendritic cells earlier. These are antigen-presenting cells that really are part of the innate immune system, but the frontline cells needed to stimulate what's called the adaptive immune system. And it's the adaptive immune system which really ends up killing the foreign invaders that come into the body. And I'm going to talk about the adaptive immune system in a second. Now, the opposite of a virus giving off a big danger signal is yourself. So we don't want to generate autoimmunity in ourselves, and we've got a lot of proteins in our body and a lot of immune cells in our body, but our immune cells are not attacking our normal organs, and that's because proteins that are presented in immune receptor molecules on our organs are seen as part of us, and there's a tolerization of the immune response. We now know that the immune response is potentially capable of recognizing those antigens. That's why people develop autoimmunity. But the way the antigens are presented to the immune system turns off that adaptive immune response, so we don't attack ourselves. Now, cancer is in between those two, and I'm going to explain a little bit more how that is. Cancer is not a virus. Cancer is really our self gone crazy. And so the immune system recognizes the gone crazy part, but unfortunately it also recognizes the it's our self part. And so the immune system may make a little bit of a response against it, but oftentimes it's the type of response that will turn off any type of immune system cell that would directly kill the tumor. So this is our big problem. With generating immunity to cancer, what we're really trying to do is cause a limited autoimmunity that just attacks the tumor. And so the big question is, how do you do that? Well, first of all, in cancer, we need to know what the antigens are. The antigens are those immunogenic proteins that your immune system is going to attack. And in viruses, it's easy to recognize those antigens because they're foreign. They're not part of our bodies. But in cancer, it's a little bit more difficult. So in the last decade, a lot of work has gone into trying to figure out what portions of the cancer are actually capable of stimulating immunity. And as it turns out, a lot of portions of the cancer are capable of stimulating immunity. You can have immune responses to proteins that are secreted by the cancer, such as a protein IGF-BP2, or if anyone in the room has cancer, there's a protein called CEA that sometimes they measure because it's shed from your cancer. There's another antigen that's common in prostate cancer. It's called PSA. Some people in the room might be having PSA tested to assess your risk of prostate cancer. That is immunogenic to the immune system. The immune system is capable of recognizing PSA, and in fact, there are vaccines that are targeting PSA. We know that cell surface proteins that are on top of cancer, so these are generally receptors that stimulate the growth of cancer. Those are also immunogenic. I'm going to specifically talk about a protein, HER2/neu, later on the talk as kind of a classic example. But other proteins like epidermal growth factor receptor or other growth factor receptors we know also stimulate immunity in cancer patients. And then finally, there are proteins that are only found in the cancer cell. These are called intracellular proteins, such as P53 or survivin. These are names of proteins, all of which are operative in cell growth. So these proteins in cancer suddenly turn on the immune system because in cancer they're abnormally expressed. So all these proteins that I'm showing you right here that are immunogenic in cancer are needed for normal cell development. You have a cell, the cell isn't going to last forever, it's going to die, it has to make another cell to do its function. The big problem with cancer is the cells never die and there's a lot of growth of new cells, and that's what causes cancer. So before I describe to you how the immune system recognizes these abnormally expressed proteins in cancer, I have to tell you what the immune microenvironment is like in cancer. And this was one of the biggest hurdles that many, many laboratories and scientists all over the United States have been trying to figure out and made great headway to understand how cancer is recognized by the immune system. Now, in the first talk, you heard about B cells and antibodies. And that's because many of the infectious disease that we have good vaccines against are directed against bacteria and germs that circulate in our bodies. And so we generate an antibody response because antibodies are immune system proteins that are made by B cells. The B cell is a member of the adaptive immune response. And these antibodies can bind to these bacteria and clear them from our system. But cancer acts more like a virus. And viruses are really attacked by the other major component of the adaptive immune system called the T cell. And the beauty about the T cell is that immune recognition of an antigen by a T cell is very, very specific. Because antibodies are specific too, but the way antibodies recognize antigens are really to bind to them externally. But the way T cells recognize immunogenic proteins is that those proteins get eaten up by antigen-presenting cells like the dendritic cells you heard about in the first talk. And those antigen-presenting cells chop up the antigen, digest it, shuttle the antigen to specific immune receptor molecules on the surface of the cell, and then the T cell will recognize these digested fragments like a lock and key. And this is an important concept, that T cells recognize only portions of antigens, because for cancer, that's going to be how we get good selectivity to the cancer without having those T cells running around recognizing antigens all over our body. So let's talk about T cells. T cells come in two flavors. The two flavors are cytotoxic T cells. These are killer T cells. And the other flavor of T cell is called a T helper cell. Cytotoxic T cells are CD8 cells. T helper cells are CD4 cells. We call them CTL. This is what this red says. And the T helper cells are called TH for T helper. The reason why cytotoxic T cells are called cytotoxic is they can directly kill a cell. So if a cytotoxic T cell recognizes an immune receptor with its fragment on the surface of a cell, it can either cause the cell to die, kind of like strangulating it, or it can inject poisons into the cell, enzymes that will destroy the cell. They're the worker bee of the immune response. They cause a lot of destruction. The T helper cell is different in the fact that it secretes cytokines or natural substances that kind of control the entire immune response. They're a little bit like the vitamin for the adaptive immune system. If they secrete type 1 cytokines, cytotoxic T cells will be called in and they'll proliferate. And the type of response you'll get is a killing response. If they secrete type 2 cytokines, and here are some examples of type 2 cytokines, This type 2 cytokines will tell the cytotoxic T cells, you're not needed, we have germs here. And instead, what will happen is B cells will come and an antibody response is made. So often, when you see infectious disease vaccines, like you heard about in the first talk, you're creating a type 2 immune response that's causing B cells to generate antibodies. But what's really needed in cancer are those cytotoxic T cells. So what happens is, when you look in the tumors of patients, and all those antigens I showed you on the previous slide, they were defined as immunogenic because patients with cancer had immune responses against them, but individuals who did not have cancer had no evidence of immunity. So that's how we could pull them out and say, this is a cancer antigen, because patients with cancer, their tumors have educated their immune system to recognize the antigen. So when investigators would go and take tumors out of patients and look at what was going on with the immune response, what they found was, instead of lots of cytotoxic T cells, there were only a few cytotoxic T cells. And there were only a few Th1 cells generating the really needed cytokines to create the killer T cells. Instead, what they found was a lot of the Th2 cells, a lot of antibodies, which try, but they're not the most effective immune response against cancer. And some of these black cells here are called T regulatory cells. And these are helper T cells that specifically proliferate when the body thinks that it's generating an autoimmune response. And what those helper cells do, these black cells, is they go in and they turn everything off, because the signals that they're getting is that I'm about to create autoimmunity. And so that's what happens in cancer. We get an ineffective immune response and T regulatory cells that are turning off that immune response because our immune system is sensing that the antigens that are being seen are self. And what we really want is a viral type response, where the type 1 cytokines are secreting a lot of, especially the cytokine called interferon gamma, because it really activates those antigen presenting cells and gets them chopping up and presenting antigen, with lots of Th1 cells secreting all these cytokines and cytotoxic T cells. And you can see in the effective immune picture, there's very little of those black cells, there's none of them, and there are no Th2. So the big question in cancer vaccines is, how do we go from the baseline immune response that we know is present in many, many patients, the ineffective immune response, and create effective immunity? And so our approach, and there are many, many approaches that are being tested now in clinical trials, was to create a vaccine specifically designed to tweak that Th1 cell. So instead of going to the cytotoxic T cells, they're kind of the end game. Instead, we're going to go to the brains of the immune system, the CD4 Th1 cell, and try to figure out how to preferentially stimulate that cell. Now, the reason why we chose to try to stimulate the CD4 T cell is because it's kind of the mastermind, and it's also the type of cell that can take the brakes off that autoimmune signal. So what I have here is a picture, it's kind of a cartoon of the entire immune response. And instead of taking these T cells, as you can see here, and making them the biggest cell in the picture, what this picture is instead doing is focusing on this antigen-presenting cell. Now, I told you that for T cells to recognize immunogenic proteins in cancer, they need this middleman, the antigen-presenting cell. What I didn't tell you is, in that ineffective immune microenvironment, the cytokines that are being secreted actually turn off the function of that antigen-presenting cell. So that antigen-presenting cell is not very effectively presenting these tumor antigens that are present in the tumor bed. But if you could get those Th1 cells stimulated so they go to the site of the tumor where all these ineffective antigen-presenting cells are, and they actually secrete cytokines such as interferon gamma, it turns out that this cytokine can cure the defects that the tumor microenvironment is creating in the antigen-presenting cell. And what happens is, if you get excellent antigen-presenting cell activation, you'll create a phenomenon that's called epitope spreading. Now, what does this mean? It means that you have a Th1 cell, let's say that's been primed by a vaccination. The Th1 cell goes to where its antigen is. That's at the site of the tumor. Its only function is to secrete those great cytokines which turn on the antigen-presenting cells and also bring in cytotoxic T cells. And the antigen-presenting cells then begin to present not only the antigen that the T cell recognizes, but also other antigens that are present in the area. So you can develop a single antigen vaccine that ends up turning on antigen-presenting cells to create a multiple antigen response. And this is the basis of autoimmunity. If anyone has multiple sclerosis, I myself have rheumatoid arthritis, probably the initial immune response that started joint destruction was to one specific antigen. But because that response was so inflammatory, the antigen-presenting cells in my joints started presenting lots of other antigens. And that's how chronic autoimmune diseases become debilitating because of the antigen spread. So the issue with cancer vaccinologists is, how do we get the antigen spread, but have it just stay in the tumor and not spread to other antigens? Because all of the tumor antigens I showed you are also found in normal cells. So we started to ask that question by trying to choose a disease. And the disease we chose was breast cancer. And the reason why we started studying breast cancer is because breast cancer is highly treatable. But one of the major clinical problems in breast cancer is prevention of relapse. You can get breast cancer even in very advanced stages to go completely away with chemotherapy, radiation therapy, surgery. But if the cancer comes back, then it's a little bit more difficult to treat. Recently, people have really subcategorized breast cancer using a variety of methodologies, defining the cancer at its roots, its genetic background. And there's one specific subtype of breast cancer. It's called HER2 positive estrogen receptor negative breast cancer, where compared to all the other different subtypes, it has a worse prognosis, despite the fact that we have some very good targeted therapy. So we decided that we would start looking at this subtype of breast cancer in particular to try to create a vaccine to prevent the disease from recurring so we could boost that survival rate up to the rest of breast cancer. And one of the things about HER2 protein expression in breast cancer is that it's dramatically overexpressed. So that is how HER2 protein is aberrant itself. It's not mutated, but in normal breast, there's only a little bit of it. And in breast cancer, there's a ton of it, 30, 40 times more than what you'd see in a normal cell. We recognized early on, and this is a study of about 100 breast cancer patients, where compared to basal levels of the protein, in their tumor they had 1+ level, that's a little bit upregulation, 2+ level, a little bit more upregulation, and 3+ level HER2 protein, that's a lot of HER2 protein. And we looked at their immune responses, their T cell responses, as well as their antibody responses against HER2. And what we found was the greater the amount of protein you have upregulated in your cancer, the more likely we are to find an immune response. And the more likely the immune response is to be of higher magnitude. So at the time, going back to autoimmune disease, we tried to figure out what is there about abundance of a self-protein that makes it more recognizable by the immune system. And there was a concept that people were testing, studying autoimmune disease. Now, I had told you, here's immune receptor molecules. They're gray on the surface of the cell. And inside the cell, this protein is getting chopped up and presented in these immune receptor molecules. Very clever people figured out how to strip these immune receptor molecules off normal cells and then strip the antigens fragments out of these immune receptor molecules and figure out what antigens were in these immune receptor molecules. And what they found was in just normal resting cells like skin cells, your immune receptor molecules weren't empty, they were actually full of fragments. And the fragments were from self-proteins. And the fragments that got put in the immune receptor molecules on your skin cells were genetically determined by the way your genetic background processed and presented these proteins and fragments. And so dominant epitopes of self-proteins in these immune receptor molecules stimulated tolerance. T cells would just go right over them and ignore them. But they found by manipulating animal models that there were epitopes or peptides that would get into these immune receptor molecules that were subdominant. Because they weren't expressed in very high levels, T cells were capable of recognizing them, but there were never enough of them on a surface of a cell to really stimulate that T cell. But what happened was when you took self-antigens and really upregulated them, had them in abundance, suddenly these subdominant epitopes got into immune receptor molecules in high enough levels that T cells would recognize them and respond to them. And so this made perfect sense to us. That's why overexpressed proteins in cancer could be recognized, because subdominant epitopes, after they were chopped up and presented, got into these immune receptor molecules in high enough levels to be able to tweak T cells that were present in the body at very low levels that were capable of recognizing them. So this to us was kind of the key, opening the latch to figure out how we would stimulate greater immune responses against self. And so what we did was, what we had to do was figure out what these subdominant epitopes were so that the T cell could recognize the tumor cell. And we used computer modeling systems that were available from infectious disease, where you could take the whole sequence of a protein and put it into a system that would tell you all the different genetic types that are in this audience, what fragment of that big protein would most likely be presented in their immune receptor molecules. And what we found was there were fragments that were almost universally presented in anyone's immune receptor molecule. And so by determining these promiscuous binding epitopes for T cells, and this is kind of what the readout of the fragment was, we would then create the fragments systemically and go into the lab and use lymphocytes that we took from breast cancer patients who donated their blood to us and test all their fragments to see if we could find fragments that really stimulated the T cell response that appeared dangerous to the T cell. And we found some. We found quite a few fragments across many different antigens. And I'm going to focus on what we did with that HER2/neu antigen. So we found these fragments, and they stimulate T cell responses in a test tube, just like I showed you one of the people in our lab was doing. How can we now test to see whether a vaccine composed of these fragments could actually prevent breast cancer without causing overwhelming autoimmunity? And for that, we turned to genetically engineered mice. They're called GEM. They're transgenic. Now, transgenic mouse models are the most unbelievable tool for cancer biologists. Many people studying how cancer grows will find a gene that they will think is important in cancer, and then they'll create a mouse that was engineered during its lifetime to start expressing that gene in abundance. And because the mouse was engineered as an embryo, the mouse is tolerant to the protein. They're just naturally bred to develop a specific type of breast cancer. And we were able to get our hands on a mouse that was developed by a scientist called Bill Muller that actually developed HER2/neu positive breast cancer. And here's a picture of one of the mice. And here's a picture of breast cancer in that mouse. And you know, mice have breasts that go down their entire body. They have a lot of breasts. And so they end up developing breast cancer in all their breasts on both sides of their body. And the interesting thing about these genetically engineered mice is when you look at their cancers, which one is human cancer and which one is mouse cancer? You can't tell the difference. They're identical. And they behave identically. The mice develop in premalignant lesions and then invasive ductal carcinomas. The new protein is markedly overexpressed on the mouse breast cancer, yet basal levels of mouse new are found everywhere else in the mouse's body. So this was one very powerful way we could test whether we could stimulate an immune response against self with a vaccine, whether stimulation of an immune response would cause overwhelming autoimmunity, and finally, whether it was even effective, all in one biologically relevant animal model. And so here you can see an example of about 15 middle-aged mice where we gave, in each group, at the time they were 16 weeks old, we began vaccinating them with a vaccine composed of 3 antigens expressed in human breast cancer and also expressed in mouse breast cancer. Many of these important proteins are conserved across species. And you can see at about a year, 40% of, 60% of the mice were without cancer, whereas every single one of the control animals had already developed cancer. So this, and the mice were safe, they were well, they didn't lose weight, there was no evidence of autoimmune disease in any of their tissues. So we were able to say at this time, all right, we've got a concept. This fragment vaccine works, it's safe, it's effective, and we also discovered that we could generate those type 1 T cells in the mouse. So we had a very effective biomarker to go into clinical trials. And at that point, we stopped. We made an application to the Food and Drug Administration for what's called an investigational new drug and asked them if we could run a phase 1 clinical trial in patients with advanced stage breast cancer. And then the fun began. And this is really the bench to bedside research. So we've been doing all this in mice and work is going around fast. And now we're going into humans and the questions start piling. How do we design a clinical trial? How do we make the vaccine? How do we go from a vaccine in a small number of patients to a vaccine in a large number of patients? And so this is really the basis of the clinical trial process. Now, we're fortunate here at University of Washington because we have what's called a GMP facility, and this means a good manufacturing practice facility. So if you have a great idea at the University of Washington about making some type of drug or even device, you can go to this facility, and if you have a grant, they'll make it for you. And so here you can see this is all behind glass. You know, it's a manufacturing facility. Everyone's dressed up just like you'd see in industry. And basically, they take your idea, they take the raw substances, and they create a vaccine. And so I'm going to show you down here the clinical trials process. And it really spans 4 phases. The first phase is called phase 1 study, and I've just shown you all the animal and laboratory studies. They take about 4.5 years. For our vaccine development, they take about 2 years. And then we do phase 1 studies. Phase 1 studies have about 15 to 30 patients in them, and the major endpoint of a phase 1 study is making sure it's safe in humans. After you get the result of your phase 1 study, you go on to a phase 2 study. And those are usually fewer than 100 patients. They take about 6 years or less, usually about 5 years. And then a phase 3 study takes hundreds of patients. And those usually take, 5 or even 6 years. And then after a phase 3 study, and I'll talk about that in a second, that's designed to show that the intervention you're doing is better than standard of care, you can go ahead to FDA approval. So you can see, you can generate a lot of really great ideas in 2 years, but now you've got an 8-year period or a 10-year period of very intensive testing to get that idea to clinic. So not every idea that you have in the laboratory is going to go to clinic. So what happens at each clinical phase? Well, phase 1 is a very difficult phase of testing. You're testing for safety and toxicity. you're not testing for clinical benefit. In fact, all you have is your preclinical animal data. So many times you go ahead to the patient and you say, we don't even know whether this is going to help you or not. We hope that your participation is going to help others, but we're not sure if it's going to help you. So as you can see, less than 8% of all cancer patients go into clinical trials, and 65% of them usually go into phase 3 clinical trials. So you can see phase 4, out of that 8%, only 14% ever volunteer for this phase 1 clinical trial, largely because there's no guarantees. And you can imagine, we're going to hear from a patient in a second about hearing someone say, we don't know if this is going to hurt you, but we're pretty sure it's not going to help you. That's kind of, who'd volunteer? Phase 2 is really focused on clinical benefit. And so we know that it's safe, it's probably not going to hurt you. We're still going to get further data on safety, but now we want to see whether it does anything against your cancer. And then phase 3 is taking this new drug and comparing it to standard therapy. And if that result is statistically positive, it may be approved for clinical use. And so this clinical trials process is very long, and it's made longer by the fact that most patients with any disease, not just cancer, just don't volunteer for phase 1 clinical studies for a variety of reasons, not just because they're unsure what's going to happen with them. In fact, many cancer patients, when they do see a phase 1 study, they want to be involved because they're hoping it's going to help them. And many of them have gone through this process of having cancer, and they're really dedicated to trying to help others. So I'm going to show you one result from a phase 1 study where we had some long-term follow-up. And I want you to think back to all that animal data in those cartoons I showed you about the antigen spreading and the Th1 responses. So we created a peptide-based vaccine, that's a fragment-based vaccine, and we immunized women with very advanced stage breast cancer, some of them with stable disease, some of them in remission, but all of them with metastatic disease. And what we found was that we were able to generate immune responses in about 80% of the patients immunized. And the immune responses were that Th1 response. In fact, when we compared the immune responses in the cancer patients against HER2/neu to tetanus, because we gave them all a tetanus shot, they were at the exact same level. So these were very robust immune responses. We potentially made the cancer look dangerous. But the interesting thing was we tested them against the fragments that they were immunized with. And here you can see in black, these bars, the percent of patients that responded against their immunizing fragments. But in gray, you can see the percent of patients who responded against fragments of the HER2/neu protein they weren't immunized against. And this is epitope spreading. Basically, the gray bars reflect that the antigen-presenting cells were turned on by that Th1 driver clone, and the gray bars are representing a natural processing of the HER2/neu protein and presentation of that protein endogenously. And subsequently, on a follow-on study to this, we demonstrated that the patients began to develop high levels of immunity to other immunogenic proteins besides HER2/neu that they were immunized in their tumor. Lupe Salazar, Dr. Salazar and a group recently went back to this study, which was published in early 2000. So we have 10-year follow-up on these patients and found that these very advanced stage breast cancer patients were still alive. And the trial predated the use of trastuzumab, which is a monoclonal antibody directed against HER2/neu. And what we found was about 40% of the patients were still alive. And when we went to our statistician and said, what immune response, what anything predicted this really unusual long-term survival, they said, well, whether they had chemotherapy was an independent predictor of survival, and whether when they were vaccinated they had progressive disease or stable disease or no disease, that was an independent predictor of survival. But whether they developed epitope spreading or not was an independent predictor of survival, meaning correcting for all other things that could contribute to this unusually long survival. Epitope spreading really indicated it. And here you can see epitope spread patients enjoyed a median survival of 84 months. That means half are still alive and half have succumbed to the disease. And when you look at the patients who didn't develop that immune marker, most of them just had the natural course of metastatic breast cancer. And so this type of data has really revolutionized the way cancer vaccinologists think about measuring immune responses with cancer vaccines. And subsequent to this data, many people in melanoma and immunizing against other cancers have also validated that the development of epitope spreading after vaccination, this limited autoimmunity directed against the cancer, is a good marker for people who are clinical responders. Here I'm just showing you a second study now really taking a homogeneous population of stage 4 breast cancer patients all at the same time. This is a phase 2 study demonstrating not only that they respond to HER2/neu after HER2/neu vaccination, but also 2 other immunogenic proteins in their tumor. So this is antigen spreading outside of HER2/neu. And again, in these very advanced cancer patients, the median overall survival hasn't even been reached yet. So again, an unusual long-term survival. So this vaccine is now poised to move into a phase 3 study where you're really comparing it against standard of care. But again, the development process for that was a 10-year process to get to the point where there's enough data to try to launch it into a very large study. In the final 2 slides, I just want to make 2 more points. And the first point is, outside of the excitement of antigen spreading, I think one of the other exciting things about bed-to-bedside research is the spreading of ideas on how to vaccinate to other groups. And having a community of people studying cancer vaccines, trying to take those ideas and do them in different ways. So I want to highlight 2 other investigators. One is George Peoples at Walter Reed, looking at immunizing against HER2/neu, not in advanced stage cancer patients, but in women with very early cancers. And what he showed was he could see a survival benefit immunizing in stage 1 and 2 disease. Moreover, he saw a survival benefit even when the tumors expressed that 1+ level of HER2/neu. So his data has shown us almost anyone with any overexpression of HER2/neu might benefit from vaccination. And the final investigator I want to show you is Brian Sersnicki. He's at University of Pennsylvania. He took the concept one step further and took some of the peptides that we had identified and moved them into patients with ductal carcinoma in situ. That isn't even invasive breast cancer. That's a pre-malignant disease. It's the most common non-invasive breast cancer that's diagnosed in women today. And as you can see, when he immunized patients prior to having them have their DCIS taken out, he was able to generate downregulation of the HER2/neu protein in almost all patients with DCIS. And here you can see an example of the pathology where they have now turned into HER2/neu negative DCIS, which is a much lower risk for progression to invasive cancer. And in fact, in about 30% of patients, he's a surgeon, when he went to take out their DCIS, it was no longer there. So these are also very good evidence that breast cancer vaccines, especially targeting HER2/neu, are going to move ahead in the future. And so finally, this last slide, again, I wanted to emphasize to you, I am one person getting up and representing lots of different people. In fact, there are a couple of people from the lab here today. And when you're talking about doing translational science, it's really not, a guy in a lab with 2 graduate students. It takes a team, and it takes a team of very sophisticated investigators. And I think a lot of time people with science think that everyone's super competitive with each other and they don't want to share data. And with translational research, that's exactly the opposite. If we're not sharing data, like I said, only a few ideas will be able to take to this very long clinical trials process. So we need to really be able to come together as a team and vet those ideas and talk about those ideas. And in fact, we kind of think of our team as not only scientists and students and nurses and drug developers and things like that. This is what this group represents. But also our major collaborators are the patients who will take the courageous step to volunteer on a new frontier of treatments that were never tested in humans before. So at this point, what I'd like to do is introduce Roberta Huffmaster. And Roberta is, come on up here, Roberta, because we're gonna talk and have these guys ask you some questions. Roberta has got breast cancer, and she's got metastatic breast cancer, and it's HER2 positive. You were diagnosed in 2008.
2007, actually.
2007.
Mm-hmm. Stage 3.
And so you can see that, you know, this is how breast cancer works. And she is in a clinical trial in our group that's kind of a next gen of cancer vaccines. And this is for patients where their disease can still be measured. And in this clinical trial, we're using vaccination to very quickly generate T cells that we can measure in the blood, and then take the blood out of the patient and take those T cells, go into that GMP facility with them, grow them up to great numbers, and then go back and infuse them into the patients. So after vaccination, in some of those slides that I showed you, the T cell response, the HER2/neu specific T cells, about 1 in 8,000 of the circulating white blood cells are HER2/neu specific T cells after vaccination. But after this strategy of growing up the T cells in great numbers and infusing it into patients, that's called adoptive T cell therapy, about 1 in 100 of the white blood cells are now capable of recognizing HER2/neu. And so the differences between protecting you from minimal exposure to a virus versus if you had an overwhelming infection, your T cell precursor frequency would be like 1 in 10, 1 in 20 of your T cells are batting the virus. So since cancer isn't dangerous, we're manipulating the T cells and then putting them back into patients to overwhelm their cancer with a very effective immune response. But it had never been done in breast cancer patients before. It had never been done with HER2/neu before. And we're basically talking about making 1 in 100 of her T cells capable of recognizing herself. So you were consented by Lupe, and she went over all that for you. What went through your mind when you really sat down and you're looking at her and she's going through all that stuff for you?
I've tried a number of other trials, either applying for them and not qualifying for them, or starting them and failing to meet the criteria. I've also had numerous rounds of chemotherapy, which have only resulted in further metastatic disease. So I came up to this trial with hope that I might be able to benefit from it personally, as well as contribute to the body of research, in the hopes that metastatic disease won't be an issue for so many women with HER2/neu.
You talked about the process of getting into a clinical trial and that you had tried many before. Can you tell us a little bit about that process?
There's a lot of research that I've done as an individual in order to seek out trials, and I have to say that that's probably been the only way I've found out about trials, is from some of the many research tools that are out there and let you know about trials. And then coming from a medical background, I've been able to sift through those that I think would be applicable to me, number one, and number two, what I'd really be interested in, and number three, what I might be capable of following through on. So that's the initial process, and then contacting persons like you, Dr. Disis, to find out if I could have an application to have my records submitted so that you can look over and see if I'm an appropriate candidate, and then coming up and meeting with staff to go through further diagnostic testing, be it labs, scans, to see if I meet the criteria. And I did that, trying to get into a trial back in New York, actually at Memorial Sloan Kettering. I flew back there 4 times in the attempt to get into that trial, and I was unsuccessful. So then I sought out a trial at UC San Francisco that was a takeoff on the Ty-curve in increasing doses, and I found I was unable to tolerate that. And then I found out about a TDM1 trial, which is Herceptin, which has now been tagged with a chemo drug, and I was in that trial for about 3 months and thought I was doing really well when they found progression of disease. So at that point, my options were go back and look at aggressive chemotherapy, do nothing, or continue in my search for a clinical trial. And I was fortunate enough to get into your trial. I've been off of Herceptin and all other forms of chemo for about 5 months now. I feel very good, and I don't know what the scan that I had 2 weeks ago actually showed, whether there's progression of the size of the tumors or not, but this is where I feel like I need to be, and I'm very grateful for this opportunity.
Let me ask you this, you know, when you're looking for all different types of clinical trials, and there's a lot of tools that are out there, you know, I go on it as a physician and I'm overwhelmed with the information. I mean, half of the stuff I can't understand, you know, and this is my business. So how do you sort through that? Who do you ask to help you with this? I mean, how do you figure out all this complicated jargon that's in those things? What would be the best thing to do?
I've had the ambition to be in a vaccine trial for a number of years because one of the first persons I spoke to after receiving the diagnosis of HER2 was a woman who was in the trial back in Pennsylvania, and she contributed her success in staying free of disease for a period of years at that time as having been in that vaccine trial. So I've had that in the back of my mind even before I had metastatic disease. Unfortunately, I hadn't been able to find one for a while. But to answer your question, I don't know that I do understand all the jargon. I just do the best I can with my limited knowledge in looking at some of the drugs that are being offered, comparing them to what I've already been on, looking at whether I want to go through that type of possible side effects by putting myself through it if I'm not in, if I am in remission at the time. And now I'm kind of down to the level of I'm not in remission, and I don't feel like I had too many other options other than to do nothing or to seek out another trial that was a totally different approach from what I've taken in the past.
Well, thank you.